Welcome to the video on graphing parabolic functions. First of all, let's get some vocabulary out of the way. A parabola is somewhat of a U-shaped object. Technically there's more science to it than that, but we'll be general here and just say that that's the general shape of a parabola. We study parabolas in the context of where they are on graphs. Here's some vocabulary. Where the parabola turns directions, we call that the vertex. Where the parabola intersects the x-axis, we call those x-intercepts. Where the parabola crosses the y-axis, we call that a y-intercept. And the line that cuts the parabola into two equal halves is called the axis, or sometimes known as axis of symmetry. Parabolas can have a concavity of down for their direction, or up. Some parabolas don't have x-intercepts. Some have one. Some are wide, some are narrow. There's a whole variety of different characteristics of a parabola. In our context, we'll be looking at the equations of parabolas and try to deduce those characteristics. In general, we say that the parabola has the quadratic polynomial ax squared plus bx plus c as its equation, and our goal in this video is to analyze how the different values of a, b, and c affect all those characteristics of the parabola. So let's talk about the different equation formats of a parabola. Here's an example. This parabola, as it turns out, has an equation that can be written in three different formats. Now, we haven't gotten to the part of the video yet where I teach how to graph parabolas, so don't feel like you should know how these equations are connected to this parabola. But suffice it to say that all three of these equations, if graphed, would give the same parabola. They are essentially the same equation. Before we go on, let me say a little bit about that. When I say that they're the same equation, one could argue, well, they clearly don't look like the same equation. But by same equation, we mean if you were to pick any number for x, any number whatsoever, and plug it into all three formulas, you would get the same value for y every single time you did that, regardless of your choice of x. And again, you're not supposed to see that they're the same equation, but take my word for it that they are the same equation and they do graph the same parabola. Now, these formats have names when it comes to parabola graphing. The first one is called standard form. By the way, that phrase has other meanings. If you were to Google it, you would find something different more than likely. And that's the same as the one we saw in the previous slide, y equals ax squared plus bx plus c. The second form is called vertex form, and the third form is either called factored form or x-intercept form. And each of these forms has advantages on how they relate to the graph. For example, in standard form, a very nice shortcut is that you can tell the y-intercept of the parabola immediately by just looking at the last number in the standard form equation. Great shortcut. The one disadvantage to standard form is that if you're given a parabola equation in standard form, you know the y-intercept, but you don't know the x-intercepts, the vertex, or the axis of symmetry. At least not right away. Now, if you're given an equation in what's called vertex form, you can tell by looking at the equation that the vertex is going to be -1, -8. And by the way, that comes from the opposite of this number, comma, this number. Why that's the case is a much longer story, but that is a nice shortcut for vertex form. But the problem with vertex form is if you are given an equation in that format, then you don't necessarily know much other information. You do know the axis of symmetry, though, because that has to go vertically through the vertex. But other than that, you don't know the x-intercepts or the y-intercept, at least not right away, immediately from the equation. Now, if you're given something in x-intercept or factored form, one nice advantage is that you immediately know what the x-intercepts are. It turns out they come from the opposites of these numbers. Great shortcut. But if you're given a parabola in x-intercept form, you don't know where the axis of symmetry is, the y-intercept is, or the vertex is. And so the idea is that all three of these forms have different advantages in that they immediately tell us something about the parabola, but none of them tells us everything, at least in an immediate sense. Now, in a perfect world, every math problem would give you all three. That's never going to happen, but let's say it did. If you were given all three forms, you would look at standard form and know the y-intercept. You would look at vertex form and know the vertex, and therefore the axis of symmetry. You would look at the factored form and know the x-intercepts, and once you knew all this information about a parabola, you could just rough sketch a parabola through all the points, and you'd be done graphing the problem. But of course, our situation is not so lucky that we would ever know all of these forms. You'll be given one of them, and asked to deduce all the relevant characteristics of the parabola from that one. Now, out of the three formats, the hardest one to be given, the hardest one to start with, is standard form, because it tells us very little about the parabola. And so because that's the most difficult one to start with, this video is going to be taught from that perspective. We're going to be given a parabola in standard form, and we'll have to deduce all the relevant characteristics from that one thing. Let's take a look at our first example of graphing a parabola in standard form. Here we have a parabola in standard form. Notice that gives us an a, b, and a c value. And I'm going to guide you through finding the main characteristics of this parabola one at a time. Let's start with the y-intercept. The y-intercept is always found by substituting x equals 0. And this may seem strange or backwards, but think of it this way. Doesn't every point on the y-axis have an x-coordinate of 0? And that's the logic here, why we do this. Nonetheless, plugging in 0 to the original problem and doing all the algebra gives me a value of 8. And that tells me my y-intercept is at 8. Next, let's go about finding the axis of symmetry. Here's a formula that you can use to find the axis of symmetry. Why this formula was created, why it works, or all the mathematics behind it is beyond the scope of this video. I would say memorize that formula. That's how you find axis of symmetry. There's a much bigger backstory that we won't go into here. But plugging in the b and a values from my problem and simplifying the fraction ultimately leads us to 3/2, and that's my axis of symmetry. By the way, 3/2 is 1.5, which is why my axis of symmetry is right here between x equals 1 and x equals 2. Next, let's find the vertex. The vertex always lies on the axis of symmetry, and because it does, it's going to have the same x-coordinate as the axis of symmetry. So to find it, I simply take the original problem and plug in the axis of symmetry value into the equation. Now, I did all of this on scratch paper, and eventually, after much work, I got 25/2. If you're not comfortable with fractions, you're going to want to pause the video and work that out, and then compare it to my scratch paper. Here's my scratch paper, and we'll move on from there. But what that tells me is that my y-coordinate of my vertex is 25/2. But I already knew that the x-coordinate was 3/2. Therefore, my vertex is 3/2, 25/2. Where is 25/2? Well, 25/2 is 12.5, which is why the vertex is up there, a little bit off the amount of space I allotted on the graph. And for our last characteristic, let's find the x-intercepts. X-intercepts are always found by substituting y equals 0. And again, while that may seem backwards, think of it this way. Every point on the x-axis has a y-coordinate of 0. So substituting y equals 0 into the original problem gives me this. But now to find my x-intercepts, I've got to solve for x. You may have experience in this matter, and if so, you know about the quadratic formula, which I used to solve this equation. Now, I didn't show the work in this video, but I did get -1 or 4 as my solutions. If you're not comfortable with the quadratic equation, you can go to my video series on solving quadratic equations. It's a 4-video series. You can look at either video 2 or 3, and they'll thoroughly explain how it is that I got -1 or 4 as my 2 x-intercepts. And so, plotting those points, here they are, -1, 4, are plotted on the x-axis. Now, I've gathered all of the information that's pertinent to a parabola. And generally speaking, it doesn't matter what order you find it in. But here's where I find myself now. I know roughly where my parabola is going to be because it has to pass through those 4 points. And it also has to turn at the vertex. And since the vertex is the turning point, in this case it's got to be the top of the parabola, or the maximum. And therefore I know that my parabola will be right there, and now I have a sketch of my first parabola. Let's take a look at our second of 3 examples of graphing a parabola in standard form. Once again, I'm in standard form here. I have my a, b, and c values. Let's go through the same steps to find the key features of this parabola and plot them. First, the y-intercept. Always found by substituting x equals 0. Here's the original problem with 0 plugged in. Do some algebra, and the y-intercept is 7. This shouldn't surprise us. After all, we learned earlier in this video that when in standard form, the y-intercept is always the so-called c value, which in this case is 7. So, plotting that, I've now got my y-intercept. Moving on to the axis of symmetry. Here's the formula for axis of symmetry. Again, mathematicians derived this. Most students don't need to think much about where it came from. It's more of a memorized kind of a thing. Plugging in my b and a values from this particular problem, I did my work on scratch paper. I did not show it here, but I did end up getting +4. So that tells me my axis of symmetry is at +4. Now earlier, I mentioned that when finding the key features of a parabola, it doesn't necessarily matter which order you go in, and for the most part that's true. But I will always find the axis of symmetry before I try to find the vertex, because as you may recall, finding the vertex requires plugging in the axis of symmetry value into the original problem. Notice I've plugged 4 into the original problem here. I worked all of this out on scratch paper, not shown in the video, but it did work out to -1. Now that's the y-coordinate of my vertex. I already knew that the x-coordinate was 4 from the axis of symmetry. Therefore, my vertex is at 4, -1, which is right here. And for the last key feature, let's look at the x-intercepts. X-intercepts, again, are always found by substituting y equals 0. Here I've put 0 into the original problem for y, and now I've got to solve this equation to find my x-intercepts. Well, in order to solve this equation, I could use the quadratic formula with the current a, b, and c values of 1/2, -4, and 7. There'd be nothing wrong with that, but I don't like dealing with fractions when I don't have to. So I'm going to use a trick here that allows me to double the entire equation. Notice I've times the whole equation by 2. This is not mandatory, but it sure makes the work easier. And now, substituting my new a, b, and c values into the quadratic formula, I eventually get these 2 values. Now there's a lot of work that went into those. And I didn't show any of it in this video, but you can look at my prior video series to see the kinds of work that led to these kinds of solutions. But now to plot these points, how can I do that? These are my x-intercepts. Where on earth is 4 minus radical 2, or 4 plus radical 2? Well, radical 2 is about 1.4. And while I have that memorized and most students don't, you can still estimate it by just guessing a number times itself that equals 2 and get a rough estimate, at least to know that it's 1 point something. I used scratch paper and worked out the x-intercepts as about 2.6 and 5.4, which puts them right about there on the x-axis. Now, what I have is these 4 points that my parabola must pass through, but keep in mind the vertex is my turning point, which in this case has to be the bottom. And since the vertex is at the bottom, by the axis of symmetry dividing the parabola into 2 equal halves, I have a rough sense of where my parabola will be. That's the second of 2 examples. Let's take a look at this, our third of 3 examples, again in standard form as you'll notice, and we'll go through the same steps one more time. The y-intercept is always found by substituting x equals 0, which in this case, like the last problem, was 7. The x-intercept, the axis of symmetry, is found by this formula, which you should memorize. Plugging in the b and a values from my original problem leads me to an axis of symmetry of -2, which is here. To find my vertex, I plug in my axis of symmetry value to the original problem. I didn't show the work, but that all worked out to 3 on my scratch paper. And that's the y-coordinate of my vertex. Therefore, my vertex is -2, 3, which is here. And lastly, my x-intercepts. X-intercepts are found by substituting y equals 0 into the original problem. Now, to go about solving this, I use the quadratic formula. And again, I'll refer you to a prior video if you feel like you need more detail. But I ended up getting -2 plus or minus I radical 3. You may recall that I is the square root of -1, which arises whenever we have a negative under the radical in the quadratic formula. Long story short, I have imaginary terms in my x-intercepts. They're not real numbers, and therefore the conclusion, as you would see if you looked at video 3 of 4, is that there are no real x-intercepts here at all. That means this parabola doesn't cross the x-axis. Now that's not surprising. After all, the vertex is the turning point, and I have to get through the y-intercept. If the vertex is my turning point, and I have to pass through the y-intercept, the parabola must be concave up and look something like this. Now I am done with the 3 examples, and you have enough information at this point to graph any parabola in standard form. I'd like to go a little bit beyond that and delve deeper into 2 of the problems that we already did. I want to teach you something that I call the 1A, 3A, 5A trick. I've completely made this name up. No other math teacher calls it this. You won't find this anywhere referenced as the 1A, 3A, 5A trick. But here's what it is. Let's look at it in reference to one of the problems we graphed earlier, which is right here. Okay, remember earlier when we found the axis of symmetry as 3 halves and we plugged that into the formula to get the y-coordinate, or 25 halves? Now, once you find the vertex to this parabola, suppose you just wanted a rough sketch and you didn't necessarily care about the x-intercepts or the y-intercepts, which is often the case. You can use the 1A, 3A, 5A trick, which I'll show you in a minute, to get a rough sketch of the parabola just by knowing the vertex and nothing else. So here I've plotted the point 3 halves, 25 halves. We saw this in a problem earlier in this video. And here's the logic. Here's my a value. Now it turns out, cool fact, whenever a is a negative number, the parabola is going to be concave down. So I know that this vertex is the top of my parabola. And at this point I could just draw a parabola opening downward with its peak or maximum at the vertex and have a rough sketch of what the parabola would look like. But how wide is this parabola? Or how steep is it? Well, to answer that question, what you do is you multiply a, which in this case is -2, you multiply a by 1, by 3, by 5. Notice these numbers in green, -2, -6, -10. Watch how I can use those numbers to find other points on this parabola and get a rough sense of where the graph is. Alright, I direct your attention to the vertex. Watch this. I'm going to go over 1, and then because of my -2, I'm going to go down 2, and that's going to give me 2 points on my parabola. Then, widening out one more space, my parabola will be 6 spaces lower than that, leading me to the next 2 points. And then from there, widening out one more space in each direction away from the center, my 1a, 3a, 5a trick tells me I'm going to be going down 10 to get to the next 2 points on the parabola. And you can see how the parabola continues to get steeper and steeper as you spread outward away from the axis of symmetry. Now notice, I don't have the x or y intercepts here, and if I don't want them, that's okay. If you're not asked for them, then these points are enough to guide your parabola. You can simply draw the parabola through those points and have a rough sketch of where it would be. Let's look one more time at the 1a, 3a, 5a trick in relation to another problem we've already seen in this video. In this problem, we found the axis of symmetry was -2. We plugged -2 into the problem and got the vertex. And now that we know the vertex is -2, 3, if we want a rough sketch of this graph, we don't necessarily need the x-intercepts or the y-intercepts. We can use the 1, 3, 5 trick. Notice in this problem a is 1. By the way, as a side note, whenever a is a positive number, as it is in this case, the parabola is going to be concave up. Here's my 1 times a, 3 times a, and 5 times a for this particular a value of 1. And I can use that 1, 3, 5 to get, in some sense, an average rate of change in my parabola. Now remember, my parabola is concave up this time. Watch starting at the vertex. I can go over 1 and then up 1 to get the next 2 points on the parabola. And from those 2 points, I can go outward 1 again, and this time up 3 to get the next 2 points on my parabola. And from there, I can go outward 1 more space and up 5 to get to the next 2 points on my parabola. By the way, this trick doesn't end at 1a, 3a, 5a. If you wanted to keep going, you could call it the 1a, 3a, 5a, 7a, 9a trick, because it's the sequence of odd numbers that will perpetuate this parabola to get steeper and steeper. Most people don't go past 5a, because once you have those points, even though we don't have the x-intercepts or the y-intercept, although we kind of do in this case, but we didn't need to find them specifically, this information is enough to graph the parabola, and that completes the 1a, 3a, 5a trick, and that completes the Graphing Parabolas video.